Now here, one more example, somewhat important and somewhat it is critical also. Some difficult is there. So that the set G of all order pairs AB of real numbers for which A is not equal to 0 is a group with respect to the operation cross defined by AB cross CD is equal to AC, comma BC plus D. First, we have to know the set. What is set G here? G is set of all order pairs bracket AB of real numbers for which A is not equal to 0. So G contains order pairs like this AB. AB are real numbers and A is a non-zero number. Here binary operation is defined by AB cross CD is equal to AC, comma BC plus D. We have to show that G is a group. Here, closure property, let us take two elements in the set G. So bracket AB, comma bracket CD belong to G. Then AB cross CD is equal to, by definition, it is AC, comma BC plus D. This element belongs to G since AC is not equal to 0. What is the condition for the elements in the set G? A is a real number, B is a real number, and A is not equal to 0. It is given. So here, A is non-zero number, C is non-zero number. So the product AC is non-zero. AC is a real number, BC plus D is a real number. So this element belongs to G. So closure property is satisfied. I will write thus G is closed with respect to the binary operation cross. Next we take three elements for associative law. Bracket AB, comma bracket CD, comma bracket EF belong to G. I am taking three elements in the set G. Here A is non-zero, C is non-zero, and E is non-zero. A, B, C, D, F are real numbers. First I will put bracket for the two elements A, B and C, D. So I will put another bracket called square bracket. Square bracket AB cross CD cross EF is equal to. From the definition I will write AC, comma BC plus D cross C cross EF. And again using the definition for these two elements I will write ACE bracket BC plus D into E plus F. So after multiplication we get ACE, BCE plus DE plus F. On the other hand, the right side part AB cross square bracket CD cross EF is equal to AB cross, applying definition for these two, we get CE, DE plus F. Again operating these two elements, we get ACE, BCE plus DE plus F. These two are equal. Therefore, associative law is satisfied. So I will write square bracket AB cross CD cross EF is equal to AB cross square bracket CD cross EF. Thus, associative law holds good in G with respect to binary operation cross. Next, we go to the identity element property. Let us take any element AB in the set G. Also, 1, comma 0 belongs to G. By observation, I am taking this element 1, 0. 1 is a real number, 0 is a number, 0 is a real number, and 1 is not equal to 0. This element belongs to G. Operating AB and this 1, 0, we get AB cross 1, 0 is equal to, by definition, we get simple, it is AB. And 1, 0 cross AB gives AB. So by operating 1, 0 with the element AB on the right side and on the left side, we get the same element AB. Therefore, we say that 1, 0 is the identity element in the set G. 1, 0 is the identity element of G. Next, we go to the inverse property. Let AB belong to G. I am taking an arbitrary element. That means any element in the set G. By observation from the closure property, I am taking 1 by A minus B by A element in the set G. Here 1 by A is a non-zero number and this is a real number, this is a real number. So this element belongs to G. Operating with the element AB, AB cross 1 by A comma minus B by A gives A into 1 by A comma B by A minus B by A. This is 0. So we get 1, 0. On the other hand, operating from left side, we get 1 by A minus B by A cross AB is equal to 1 into A by A minus B plus B. This gives 1, 0. So here we observe that 1 by A comma minus B by A is operated with the element AB from right side and from left side. We get 1 0. That is the identity element. So this is called inverse of this element AB. So I will write therefore inverse of AB is 1 by A minus B by A. Here we are taking AB, any element in the set G. That means inverse element exists for any element. That means each element has an inverse. So I will write inverse element exists for each element of G with respect to binary operation cross. And with this is a group. But this is not an abelian group. I can write, already we have verified 4 axioms. So I can say this set G is a group with respect to the binary operation cross. Here one important point is, in the previous examples we have seen groups with commutative law, abelian groups. Here this is a group but not commutative. That is important point here. Let us take 2 elements in the set G, AB, CD. AB cross CD gives by definition AC, BC plus D. And CD cross AB gives CA, DA plus B. Here first element is, first component in this is AC and here it is CA. Of course these two may be equal, but the second component is BC plus D and here this is DA plus B. These two are not equal. Equal means two parts must be equal. First component, second component. Here first component is equal but second component is different. Here this is BC plus D and this is DA plus B. So these two are not equal. So I will write AB cross CD is not equal to CD cross AB. Again, AB cross CD is not equal to CD cross AB. Therefore, commutative law does not hold here. There is no commutative law. So here G cross is a group but not commutative group. This is one important example. If anyone asks, give an example of a non-abelian group, non-commutative group, student has to give this example. This is the example for a group but not commutative. Here, this one. I am taking a set G of order pairs AB of real numbers for which A not equal to 0 and a binary operation defined AB cross CD is equal to AC, BC plus D. With this binary operation, G is just a group but not commutative. So this is an example of a non-commutative group.